I have to be up by midnight, till midnight to upload. Okay, so now can anyone give us the y coordinate of Q?
F of x h.
Thank you. Say it again. F of
X plus h.
Yes, in parentheses. So notice perfectly you said not f of x plus h. That would be terrible. You said correctly f of x plus h. So now the x coordinate is x plus h. The y coordinate must be the function value when I plug in this number. If this number is 5, then f of 5. If this number is 15, then f of 15. Excellent. Okay. And now I would like us to identify the average rate of change of function f of x between p and q. The average rate of change of function f of x between p and q is denoted by average pq and is the slope of the line passing through the 2 points. This is called secant line PQ. So the secant line PQ has nothing to do with trig. It's just the line that crosses the graph in 2 points. Okay. Can anyone give us the slope of this line? We used the definition of the slope last time. Let's say Lake, can you give us the slope? And I will write it.
Can you repeat what I'm finding?
Yes, the slope of this line.
I can't remember. It's on the tip of my tongue.
Okay, can anyone help us?
Wouldn't it be f of x plus h minus f of x over x plus h minus x?
Awesome. Great job. Who was that?
Amanda.
Thank you. Great job. This is the slope. Now you notice that positive x with negative x, goodbye. So this is f of x plus h minus f of x divided by h. So what does the average rate of change of this function represent? And what is its measurement unit? So first of all, the average rate of change of this function between these 2 points is basically, as we wrote it, rise over run. The rise is this piece. How much I go up or down. I graphed a function, a secant line that has a positive slope, but I can graph a different function with a secant line that is decreasing, right? So this says that when x increases by this much, y increases by this much. So as x increases by h, y increases by this difference. And this is the average rate of change of the function between p and q. Now stay with me because this is half of the, basically, and I'll come back to it many times, this is half of chapter 2. Right here, right now. So now, going back to our graph. So here's our function f of x. I don't want to go back to that graph, to that page. That's why I graph it again here. So here's our point P, and here's our point Q. And we drew this. We don't have to draw this. We drew it because I want you to see what this represents, but I don't have to. The average rate of change between P and Q is still the same. The rise over run, how much this Y increases versus over how much is X increasing. Okay, but now Q is extremely close to P. So this was when we zoomed in to find the average rate of change between P and Q. But now here, this is the actual situation. P is here and Q is very, very close. Because this distance is tiny bit, like 0.1 or 0.01 or tiny. So if this is P and this is Q, obviously this is the secant line. But would you agree that this kind of looks like a tangent line? This was a secant line. And you can say, but isn't that the same graph? Yes, it is. So when I zoom in, I see that the line crosses the function in 2 points. Well, now I'm zooming out, and when I zoom out, I kind of see that P and Q, they're so close to each other that this becomes the tangent line. And the average rate of change here is the slope of this line. The average rate of change here is the slope of this line. But the difference, they're the same, but the difference in explanation is that since h is small, then the secant line is close to a tangent line at P. So this is what the average, this is what the next step is. So this was initially the average rate of change, but now we identify the fact that age is very small, and we call that difference quotient, which is f of x plus h minus f of x divided by h. So if we look at it from the from zooming in, when we zoom in, we say it's the average rate of change of the function between those 2 points, rise over run. How much it goes up versus how much is the run. But now when we realize that age is very, very small, we will say, oh, this average rate of change is actually, because age is so small, it's actually the difference quotient. Okay, what's the big deal? The big deal is that the difference quotient is almost, not quite, and you will see what that means later. Almost, I'll put in parentheses, not equal to the instantaneous rate of change. Instantaneous. Okay, what's the difference between average rate of change and instantaneous rate of change? What's the big deal? That's what we are discussing in calculus. We are really, really interested in the instantaneous rate of change. And everything we'll discuss in calculus will be based on this, on the difference quotient. And now the question also is, okay, fine. So why are we talking about this now? We're talking about this right this moment because number one, I want to review with you evaluating functions. So we established those concepts from the beginning. Number two that I want to review with you is finding and fully, it is a double L here, fully simplifying the difference quotient for different functions. And that will bring me to this last problem here. Okay, in summary, one more time. Let me switch for a moment so you can see me for just a couple of seconds. I'm driving to New York, not in the snow, but I'm driving to New York, and you ask me when I come back, you'll say, tell me what was your average rate of change. What is that? Speed, right? The average rate of change between Wilmington, Delaware, and New York. So I will measure the distance between Wilmington, Delaware, and New York. I will look at the time, find the difference. Let's say I passed by Wilmington, Delaware at 2 p.m. and I was in New York at 7 p.m. in the evening, right? So I'll say, okay, the distance is 120 miles and I'm dividing by 5 hours. I did not stop anywhere. That is my average speed. This is what the average rate of change is. So every average rate of change, including difference quotient, measurement unit, is composed of two measurement units. If you ask me, what is your average rate of change on that distance? I will say I drove at 52 miles distance over time per hour. Two measurement units. Every difference quotient, every rate of change, average rate of change has to have two measurement units. One coming from the top, one coming from the bottom. But now you are asking me, what was your speed, exact speed at your 150 miles from Baltimore? I don't know. Unless you call me exactly when I pass by the distance of 150 miles away from Baltimore and I look at my odometer, I don't know what was my speed exactly 100 and whatever miles away from Baltimore. That's the instantaneous rate of change. So I'm on the phone with you and I started my counting the miles and you say, you're passing by 140 miles right now, exactly from the moment you started. What's your speed? And I'm looking at the odometer and it says 60. That's the instantaneous rate of change, and I don't have to make any calculations for you, but you have to call me or I have to look at the odometer at that instant. So the distance with respect to time changes exactly at 62 or whatever the odometer says at that moment. That's the instantaneous. But if you want me to find the average rate of change between Wilmington, Delaware, and New York, then I'll measure the distance, I'll divide by the number of hours, minutes, whatever, and I'll give you the average rate of change on that distance. Do you understand the difference between instantaneous at that instant and the average rate of change? Okay, I'm switching now to my notes here. So,
actually, I have a question.
Yes.
Sorry.
is the curved line, is that your actual like speed?
This
over
is
time?
careful. This is very good question. Okay, perfect question. This is the distance formula or function. This is in miles, and this is time in hours. And this slope is the average rate of change. This is G in miles per hour. Miles, because the function is measured in miles. H is measured in hours. But now this right here, this number, the slope of the tangent, is exactly the instantaneous rate of change when I look at the odometer and I say, okay, it's right this moment I'm driving with such and such. So the slope of this line, slope, is instantaneous rate of change. The slope of the secant line, is the average rate of change between these 2 points. But this one is the instantaneous. This one I have to calculate. I have to have the distance, I have to have the time, and I will divide them and give you the answer. But this one I don't have to do any calculations because I have to look at the odometer. Both of them have measurement unit miles per hour. Every average rate of change and instantaneous, if it's a rate of change, will always have 2 measurement units, blah, 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 over blah, blah, blah. It can be dollars per unit. It can be number of people per year, and so on and so forth. Mandatory 2 measurement units. We see on the side of the road sometimes in certain states it says 60 miles. No, we're not driving at 60 miles. We're driving at 60 miles per hour. Okay.